Let's look at a normal candle flame through a diffraction grading. I'm starting with 80 lines per millimeter. One 40. 300. And finally, 600. How can you describe the spectrum? Can you explain its formation? How about the differences between the different diffraction gratings? How does this compare to line spectra when we use the discharge tubes? Krypton, for example, iodine, helium. Let's look at a discharge tube. In this case, our tube has krypton. Let's look at the spectrum of krypton through a diffraction grating with 300 lines per millimeter. What do we expect to see? How can we explain it? So I'm bringing in the diffraction grating, and there we go. Okay, let me just center that. So look carefully at this. How can you describe this? How does it differ from a similar spectrum if we had used a candle light or a white light source, normal light bulb? Do we expect to get the same lines if we use a tube containing a different gas? So I'm going to replace the krypton tube, change nothing else, with another one. Let's see what we get. Now we have helium. Let's see again at this. Let's have a look again at the spectrum through 100 lines per millimeter. So I'm adding the diffraction grating. There we go. 100 lines per millimeter. The spectrum of helium. If I go to 300 lines, we see this. And back to 100 lines. Let me just center that. There we go. The spectrum of helium. This is xenon through a 100 lines per millimeter diffraction grating. What do we see? How does that compare to the spectrum of white light or the spectrum of a flame? Look at it carefully. If I take the diffraction grating out and I put now the diffraction grating back in, why this happens? What does it tell us about light? What does it tell us about the energy levels of the electrons? The next spectrum we're going to look at is the one for carbon dioxide. Let's have a look at that through 100 lines per millimeter. And now we go to 300 lines per millimeter. Why do you think there's so many more lines in this case? Remember, this is carbon dioxide. There we go. 300 lines. 100 lines. You can even try and zoom in. See the finer structure if you like, or zoom out. How can we change the electronic configuration, how the electrons are arranged in an atom? Let's have a careful look at this. If I shine a green laser, nothing much. I shine a UV laser, wow, what is happening? What did the UV laser do to the electrons? What is happening now? And if I use a more diffuse source of UV, let's have a look. There we go. So let's try that again. How can I change the electronic configuration, how the electrons are arranged in an atom? If I use a green laser, I don't see anything exciting. But if I use a violet UV laser, there we go. And if I use a more diffuse source, continues to emit light. What is it emitting? Photons. What evidence does this provide for? Where do the electrons live? Where do they have their house? Quotation marks. So that we can do something like this. Here we have a partially evacuated tube where we have a cathode and an anode. Cathode, anode. This is called a cold cathode because we're not going to be heating the cathode. Let's see what happens as we increase the potential difference to a few thousand volts between them. So I'm on now 0.3 kilovolts. I'm increasing 1 kilovolt. Something has happened. We can see a green light. These are the electrons being emitted, and as I increase the voltage, the line becomes brighter. So what we're seeing actually is the first experiment that was used to discover electrons. And initially they were called cathode rays because they didn't know that these were electrons. So how are these electrons being produced? What makes them give off light as they move from the cathode to the anode? Remember, this is a partially evacuated tube. In other words, there is a gas in there. What happens to the atoms of the gas as the electrons collide with them? Hence, how do they emit light? And if I increase the voltage further, you can clearly see that this becomes even brighter.